Right, 2 for A. And what do you get for B? Right. And they're both pointing up. So next, when we have the external picture, now we can draw the internal picture cutting just to the left of B. Once again, for anywhere we're cutting on the beam, for any value of x, the cut is always x away from the left-hand side. So what is going to be, let's start with the 2 kip. What is the moment contribution around the cut edge of the 2 kip load? Right, it'll be negative 2x. So if I'm cutting here, I'm x away from 2. If I'm cutting here, I'm also x away from 2. And x can be any value from 0 to, in this case, 24 feet. So the moment caused by the 2 kip is negative 2 times x, since it's going to be clockwise around what I'm going to be calling point C. Again, I want to reiterate, point C can be anywhere along this beam. And because it starts right away, I don't need to use the bracket function there. That will always appear in any picture that I make. Right, so the distance the 12 kip load is from that cut surface is x minus 18, as long as I'm to the right of it. So if I'm at 19 feet, it's going to be 19 minus 18 is 1 foot away from where that cut is. And if I'm cutting all the way at near 24, then it's going to be 24 minus 18 is this moment arm. So it's 12 is the force times the distance of x minus 18. And I put it in brackets because if I'm making a cut to the left of it, the bracket means it's going to turn it off. It's not included in that picture, since the stuff inside here will go to 0. So if I'm to the right, it will be included. If I'm to the left, it is not included. Right, so now I want to tackle the couple that's on the beam here. It's going to be negative 24, since it's going to be clockwise. This is already a moment. 24 is already in kip feet. We don't want to actually multiply it by a distance, because we never multiply couples by a distance in the moment equations, just like we saw in 211. But we do want this to, again, turn on or off, depending if is our cut to the left of it, well, that's not in our picture. Is our cut to the right of it, then it would be in our picture. So we still want the brackets there to have that offset, and we raise it to the 0 power. That way it's 0. If we're 0 to the 0 is going to be 0. If it's anything greater than 6, then it's some number to the 0 power, which is just 1. So this acts as just a 1 or a 0 when we raise it to the 0th power. So that way we do include the negative 24 to the right, so x is greater than 6. It's not there when x is less than 6, since this whole term drops out to 0. Right, so then we want to solve this for, we're going to get EI d squared v dx squared will equal then, when we move this, everything else to the left-hand side, 2x minus 12, x minus 18, plus 24, x minus 6 to the 0th. So on the integral step, these are, again, polynomials, which is all we'll see in this class. We'll have x squared minus 6, x minus 18 squared, plus 24, x minus 6 to the first power, which I don't need to put the first there, plus C1. Okay, so the 0 goes up 1 power to 1. We divide 24 by 1, and we're left with 24 again. And then we add the C1 at the end here. When we take the second integral, we'll have 1/3 x cubed minus 2 x minus 18 cubed plus 12 x minus 6 squared plus C1x plus C2. At this point, we want the boundary conditions. So what are the boundary conditions for this one? At B, so if you go back to the first free body diagram you drew, those things that you're solving for, those determine your boundary conditions. So we had to solve for what? A and B. That's where we have boundary conditions, and that's the type of boundary conditions we have. So we have a force at A, a force at B, which means we have a deflection at A, a deflection boundary condition at A, and a deflection boundary condition at B. So we know at the pin at A, we can't have deflection, or the deflection is 0, and the roller at B, it's the same thing. So the boundary conditions are that V of 0 is 0, and V of 24 is 0. Those are the two boundary conditions. Right, C2 is 0, because when we plug that in down here, everything drops out except C2. Right, so you get negative 336 for C1. Right, so this one asks us to go a little bit further. We want to know what the slope is at A. We have this slope equation, so we know that EI, slope of A is located at x equals 0, is going to equal, and we evaluate the slope equation, in this case, at x equals 0. And the slope will always be given to us in radians by default. And we want to note, we should have noted here, with these numbers in here, we were working in kip as our force and feet as our distance. Because again, if we want to know in radians what this is, we need to know E and I. For this one, we don't have specifics, but E would have to be now in kips per square foot to match the units, and I would have to be in feet to the 4th power so that we have the right units for our slope. So whatever E and I are, we divide negative 336 by that product, and we get the slope in radians. In this case, it'll be negative, since E and I have to be positive. So a negative slope means that it's going to be down and to the right at A. Right. That part's relatively easy. The next part we can't solve by hand, but we can at least come up with the method. If we wanted to do it by hand, how would we solve for the max deflection of the beam? We know that we have a maximum, at least a local max or a local min, when the derivative of our value is 0. So if we want to know the max or the min, the local max, local min of V, we have to say its derivative equal to 0. Conveniently, we know that the derivative is the slope. So to find, first of all, we have to find where we have the maximum or minimum, and then evaluate the deflection at that point. So what we need to do, and by hand this is not easy to solve using at least the singularity method, we need to solve for what value of x is it true that theta of x is equal to 0. So this is a much harder question than finding theta of 0. We have to now find the x. And now it's hard because we have these discontinuities here because of these brackets. So by hand, this is not really an easy task to do. But we can do it numerically for this method. I won't get into all the numerics here, but looking at the plot of this, where would we guess that the maximum deflection of the beam is going to be located? So if we used F0 or some other numerical method on this, you're going to find, right, if we guessed around 12, this is going to tell us that x happens, or it's located at about 12.98, which I'm just going to round to 13 feet for these purposes. Right, so now we can go back, we can do this step by hand. How do we find the value of the deflection then, or what is the maximum deflection then going to be?
Plug in 13 into the final equation.
Right, so now we can evaluate V of 13. Since we know that's where the maximum is, this will tell us what the maximum is. So that'll be 1 over EI times negative 3,048.